Right, so good afternoon everybody, and today we are going to take a look at Hooke's law. Now Hooke's law is often called the spring law, and it's because it deals with the behavior or how a spring behaves when it is being loaded. Now springs can either be loaded and compressed or stretched, and what was noticed over the period of time that they have been investigated is that they behave in a particular way that can be described by Hooke's law. So let's get straight into it. Hooke's law states basically that the force applied to a spring, whether it is in compression or it's being stretched, so is directly proportional to the extension or the amount of compression that a spring will receive. So force is directly proportional to extension, provided the elastic limit of the spring is not exceeded. Now all springs have what we call an elastic limit, and that is the point at which the force being applied to the spring is no longer directly proportional to the extension that the spring is being that the spring is experiencing. So generally, when we look at springs in Hooke's law at the C-sec level, we look at a spring being loaded and stretched, all right, as you would have seen in the previous video where I was just demonstrating how this experiment could be conducted. All right, so if you look on the table, on the board here, force is directly proportional to extension or compression, provided the elastic limit is not exceeded. We can write that in equation form as F is, well, not equation, but in a form, mathematical form, F is directly proportional to extension. Of course, if we want it in an equation form, we have to introduce what we call a constant. So when we put the equal sign here, we must introduce a constant K, and in this case, this constant is called the spring constant. Each spring has what we call a spring constant, and it is generally a measure of the stiffness of the spring, right? The larger the spring constant value, the more stiff that spring is, so therefore it will be more difficult to stretch or to compress. The thing is, it's normally measured in newtons per meter. Those are the standard units. So for example, if a spring has a spring constant of 20,000 newtons per meter, that means that that spring should have to be loaded with 20,000 newtons of force for it to be able to stretch a distance of 1 meter. All right. Of course, springs are not always that large, so sometimes you will see at the C-sec level that the springs are in centimeters. So the spring constant might be 200 newtons per cm, for example. That means that a spring must be loaded with 200 newtons of force, of weight, or well, not often weight, but sometimes just a force, so that it can stretch 1 centimeter. Whereas if we had a spring that had a spring constant of 400 newtons per meter, that means it would have to be stretched 400 newtons 400 newtons per centimeter. It will have to be stretched 400 newtons for it to extend 1 centimeter. So the larger the spring constant, the stiffer the spring will be. Now, how do we get that spring constant? To get that spring constant, we have to actually load the spring and plot what we call a force extension graph. Now, the force extension graph is the characteristic graph that is used, the common graph that is used when doing Hooke's law investigations, right? Force versus extension, meaning force on the y and extension on the x-axis or the horizontal axis. Now, I'm going to show you now what a typical force extension graph would look like, and also we're going to take a look at what the elastic limit of an actual spring is. So let's take a look at the values first, all right, and then we can have a little idea. So these are the values here on the table that I would have gotten by completing the experiment that we would have looked at earlier, that I would have shown in the demonstration. So if you look at it, the masses were, of course, 50 grams, that's the hanger, and then I added 20 grams subsequently each time, and and found the extension, right? Now remember, this is a force extension graph, not a mass extension graph. In this case, the force acting on the spring is the weight, right? The force of gravity acting on these masses gives these masses their weight, and that's the force that we are loading this spring with. So I just did the conversion here, and therefore a 50-gram mass is 0.5 newtons, whereas as we go along, 110 grams, for example, is 1.1 newtons. So let's look at the values. When the spring did not have any weight attached to it, it was 50 cm on the marker. And then as we added the 50 grams, it extended to 51.5. So that gives an extension of 1.5. Then we added a 20-gram mass, right, which is a 0.7 newton weight, right, and the spring went from 51.5 to 52.4, which represents an extension of 0.9 cm. All right. Then, from at the 90-degree mark, when we added the first 20-gram mass, we went from 51.5 to 52.4. So the spring was now extended by 2.4 cm, and it represented a difference of 0.9 cm extension. All right. As we continue to load, if you notice, each time the masses were added, the spring extended by 0.7 cm, and then another 0.7 cm, and another 0.7 cm, until we got to the 130. At the 130 gram mass, the spring extended by 1.0 cm, and at 150, 0.8 cm. So over the period here, this region here, right, as equal amounts of forces, as every time you added 20 grams of mass, right, the extension remained at keep increasing by 0.7. But when we got to the 130, right, the extension no longer was, when we added the 20 grams, we started getting values like 1.0 and 0.8. So each time we added 20 grams, we were getting 0.7. So there was some sort of direct proportionality. Equal changes in mass give us equal changes in extension, until we got to this point here where that no longer started to happen. The values of the extension started to change. We went from 0.7, equal increases of 0.7, to now 1.0, 0.8, right? Now at that point here, right, the force being added is no longer directly proportional to the extension that the spring is receiving. All right. So if we were to plot a graph of that, the graph would look something like this. So in this region here, with equal changes in force, there were equal changes in extension up to this point here, the straight line. So between this region here, right, force was directly proportional to extension, right? And we know that because, of course, the line is straight. But just at this point here, the line starts to curve, right? And that tells you that as we add more force, the extension, the equal changes in force, like, will not give you the equal changes in extension. At this point, we said that the spring is at its elastic limit, right? It is no longer behaving elastic after that point. If we continue to lower the spring beyond the elastic limit for extended periods of time and for large amounts of force, the spring may be permanently deformed. It will stretch out and not be able to come back to its original shape. All right? The spring will have then been damaged and no longer will obey Hooke's law. So Hooke's law says that force is directly proportional to extension, right, provided the elastic limit is not exceeded. Anytime you go beyond the elastic limit, equal changes in force will not give you equal changes in extension. So what I want you to do for homework is that we are going to plot what we call a force extension graph, right, for this particular experiment. So you're going to plot the weights, right, in newtons versus these values here of extension. 1.5, 2.4, well, 0, 1.5, 2.4, 3.1. And what I want you to do when you plot that graph, and remember to observe the rules that I taught you about plotting graphs, I want you to identify the elastic limit. Mark with an X on that graph where the elastic limit of that particular spring that we're using here is. So to be clear, we are plotting the weight, which is the force, versus the extension value 0, 1.5, 2.4, 3.1, and so on, straight down to 6.3, right? But there's one thing that you need to remember, right? We need to remember that this is weight in newtons and the extension, according to this experiment, is in centimeters. And remember, at this level, we must always work in standard units. And therefore, we must convert those centimeter values to meters before we plot. All right? So what I want to see is that table redrawn, and you put in the values in meters, those extension values in meters, and then you're going to plot me a proper graph and also mark with an X, right, the value for the elastic limit. Now the elastic limit, of course, will be a force value. So we could say beyond maybe 100 or 90, sorry, in this case 0.9 or 1.1 newtons, right? The spring cannot basically take any more weight, right, and will no longer obey Hooke's law. All right, so the elastic limit is a force value, a maximum amount of force that it can take before it no longer obeys Hooke's law. All right, so basically this is what Hooke's law is. This is what our next topic is. So hopefully you, when you plot the graph, you'll be able to explain what is going on. The next thing I want you to do from that graph is find the gradient of the proportional section, of the straight line section of the graph. Okay? And that will give you the spring constant. So the gradient of this straight line section, that direct proportional section, will give you the spring constant that we need for this particular spring. So you're going to find the gradient of that section for me, the straight line section of me. Do not draw a best fit line through the points. Remember, this is a characteristic type graph. The graph is going to be straight line for a certain section, and then it's going to curve. It may curve upward or downward, but it will curve. So your job is to look at the points, see where it's directly proportional, right? Draw the best fit line to that point, or draw that straight line for that, and then curve the rest. Is that okay? That's what we're going to be doing. So please get this done for me for our class on Wednesday, and we will discuss it then. Thank you, and I'll see you in the next video.